It is estimated that Alberta's oil sands hold 165 billion barrels of oil reserves, making it the world's third largest oil reserve after Venezuela and Saudi Arabia. Current commercial methods are facing significant challenges when it comes to bitumen extraction from surface mined oil sands ores using water-based methods. For example, water-based extraction requires a large quantity of thermal energy as it involves heating up an amount of 2.5 cubic meters of water for the extraction of only 1 barrel of bitumen. Besides, the unavoidable growth of large tailing ponds that contain toxic materials including cyanide and lead, which are released during the processing of oil sands. The production of 1 barrel of bitumen yields 3.3 cubic meters of discharged tailing sludge that can leach into groundwater and the Athabasca River and introduce severe toxins to aquatic life. Because of these drawbacks, we are currently developing a process to use organic solvent for the extraction of bitumen. Non-aqueous solvent extraction of bitumen has the potential to decrease all water-induced problems while resulting in high bitumen recovery rates from a range of oil sand ores because it runs off solvents and is not water-based. In prior research, we found that the best solvent to use for the extraction process is cyclohexane. One of the major challenges of non-aqueous solvent extraction, however, is the solvent removal from the waste material after extraction, or the so-called gangue, which contains bitumen, cyclohexane, and a small amount of connate water. When the gangue is disposed back to the mining area, it is expected that the solvent concentration should not exceed 260 parts per million. To minimize the energy used for the solvent removal, a non-thermal method such as drying the gangue at ambient conditions appears to be promising regarding both removal and recovery of the cyclohexane solvent. The experiment involves drying the gangue for 2 hours at 20 degrees Celsius and 1 atmospheric pressure. The drying curve for the gangue sample shows 2 different stages. The first interval corresponds to solvent-dominated mass loss, while the second interval is connate water-dominated mass loss. These 2 stages are separated by a crossover, which takes place approximately 25 minutes after the beginning of the drying process. The crossover signifies the point at which the faster drying stage transitions to the slower drying stage. The first stage is where the cyclohexane and bitumen solution move upwards to the surface of the gangue, and when the solution reaches the top of the gangue, cyclohexane evaporates and the bitumen is deposited on the top surface as shown in the pictures. The receding of cyclohexane liquid film signifies the start of the second stage, where the remaining cyclohexane inside the gangue evaporates through the empty pores in order to escape the gangue, and this stage is significantly slower than the initial stage. In conclusion, discerning the major variables that control the gangue drying process, like temperature, is an essential part of the drying process. For example, if the temperature is high during the drying process, it can lead to the damage of the liquid film inside the gangue. Also, to speed up the second stage of the drying process, a 2-stage non-thermal drying process can be developed to recover cyclohexane in the gangue. This can be done by introducing airflow at different speeds on top of the gangue. Also, using microwave can effectively help remove cyclohexane from the gangue. Having a complete understanding of the drying process can reduce or even eliminate the environmental effects associated with non-aqueous extraction methods and assist in its implementation on a commercial scale.